Good morning, students. Today's topic of discussion is simple transition networks. We are learning grammars and parses. We have covered link grammar, chart grammar, and we have seen how to build a parse tree in a top-down and bottom-up manner. Now, the next method is simple transition network. This simple transition network method for the construction or building of the parse tree consists of developing a transition network. What is a transition network? A transition network is a diagram that comprises of nodes and arcs. Parsing would begin with a start node and it travels along the path and reaches the um, end node. How is this traversing takes place? It depends on the type of a word it encounters while parsing the sentence. When it is parsing noun phrase, if it begins with determiner, it goes this way: noun phrase, determiner, and then noun phrase verb, noun phrase 1, NP1, which accepts any number of adjectives. We can say that a the little cute pretty girl. There are three adjectives. If it encounters three adjectives, it stays in this node and accepts all the three adjectives. And when it finds a noun after the adjective, it moves from this NP1 node to NP2 node. And this NP2 node takes noun as input, and by after reaching NP2, it is clear that there is a determiner and there might be, and this adjective, please note here that it's optional. Even if adjective is now not there, only that after the determiner noun occurs, in that scenario, um, also NP1 takes you to NP2 without any adjective. So here, when you are in NP2, it could be determiner noun. How? 1 minute, students. Please give me 1 minute. Okay, sorry students about that. Here we are developing a transition network. This is known as a transition network that would parse a sentence. And this network would parse a sentence that begins with determiner and optional adjective. This is optional. Noun, determiner, optional adjective, noun. And here, from here it pops. Pops means it comes out. Means parsing is done and sentence is recognized and um, parsed. All right. This is simple transition network. This is the context-free grammar. Grammar means where it gives the rules, production rules. Uh, Context-free grammar corresponding to transition network. This transition network. Noun phrase defined as determiner NP1 means noun phrase 1. Noun phrase 1 is defined as adjective noun phrase 1. Again, noun phrase 1 defined as noun. Why we have these three rules for this? Please observe here. NP NP is leading to after determiner leading to NP1. NP1 NP1 would have adjective and it stays in NP1 as long as it receives adjectives. Once it gets a noun, it comes out of NP1 and goes to NP2 when it gets noun. That is simple transition network (STN). Recursive transition network. Simple transition network uh, is not powerful. It is very simple and it cannot describe all languages. It can describe only languages specified by context-free grammar. And recursive grammar cannot be defined by transition network. If there is a recursive grammar means what? Suppose NP1 has one noun phrase has another noun phrase or another verb phrase or another noun preposition phrase like recursion, one inside another. When transition network is extended to recursive transition network. Recursive transition networks are an extension to simple transition network and it supports uh, recursion in a language or a sentence, or we can say that more complex structures or sentences could be parsed through recursive transition network. And a recursive transition network RTN uh, structure is given. Observe here that sentence S begins, S naught finds noun phrase, reaches to S1, moves to S2 on getting verb, again finding noun phrase, reaching to S3 and ending. Within this sentence, we have two noun phrases. One noun phrase within another noun. Actually, one sentence has two, means it is a sort of, having a complex sentence. So such type of sentences could be parsed through RTN but not by STN, Simple Transition Network. And how to implement RTN in Prolog. Prolog is a programming language, and it stands for programming logic. And this RTN program in Prolog, start, after start, set state to S0, enter the sentence. Sentence is sent, analyzed, and again it is printed. Your sentence is syntactically correct. This is how in programming language that structure could be implemented. First, take the input in the form of a sentence, and that sentence is read in, analyzed, and then if it is correct, it prints a message, your sentence is syntactically correct. Start. What does start do? Write and your sentence is syntactically wrong. It can also be wrong sentence. In that case, from start you reach to this message where you say it is a wrong, and then set state as assert. These are analyzes. These are the constructs of Prolog. And here, how to move from one state to another state or one node to another node. That is by calling this transition functions. Transition S0 A comma B. When it reads A, when being in S0, it reads A B. Being in S1, it reads A B. Like that, transition functions could be defined. And these are all transition functions that have been defined in Prolog in order to implement that recursive transition network. The next type of method for parsing a complicated sentence is augmented transition network. In this augmented transition network, apart from understanding recursive sentences, it also associates some kind of memory, some memory. It associates memory to this parser. That's why it is known as augmented transition network. Transition network has been augmented with registers. Register is a memory, and what it does is, look at the structure here. There is a sentences. In sentence, we have a subject, which is a noun phrase, and type name. The actual name is Jack. Main verb found. Tense is past. Object is again a noun phrase. There is a determiner A and there is a head. Bag means a noun. A noun is the bag. And that structure is created using augmented transition network parser by allowing each network to have a set of registers. And registers are local to each network. If you have 10 networks, you would have 10 registers. Each network would have its own register. Register is a memory unit. And this NP network has registers named. And what is an NP network? Here we have NP network. NP network would have registers which are named as DT, determiner, adjective S, head, num. These are the registers that hold the value for the whole value of the sentence. Hold the value of the sentence. Whatever sentence is given to it, it tokenizes and gets individual words which are known as tokens. And if a token is a determiner, it gets stored in this register. If a token is adjective, it gets stored in this register, and so on. Example of this augmented transition network. S is the beginning. S0 on getting NP moves to S1, and when it finds verb, it switches to S2, and eh, this being when it is in S2 without any noun phrase, also it can jump to S3. If noun phrase is there, it jumps. If there is nothing, also it jumps to S3. This is how recursion could be implemented. This is how we write sentences that contains uh, multiple phrases of same type. And then here there is a noun phrase. How to implement a noun phrase? Let us look at um, the ATN, Augmented Transition Network, only for noun phrase. It is NP, NP determiner NP1, adjective, noun. Suppose if there is no determiner, in that case, NP would take the second route, would travel over second path. This is first path, this is second path. It takes second path. If just it finds the name without determiner. Girl, suppose if I say Alice, so it's just Alice here. If I say the cute Alice, then it follows this part, the cute Alice. If I say the Alice, then it follows the Alice without an adjective. This is the noun phrase structure. And tests and actions of the arc in ATN. When it is NP1, arc is NP1. Where is NP1? Here NP1. NP1 has this one, NP2, NP1. Oh, this is about noun phrase. This entire noun phrase. It has NP. NP has 1 and 2. Two roots. Okay, two links. That is written here. NP oblique 1 means the first root from NP. NP oblique 2 is the second root from NP. And NP1 by 1 is the first root in NP1. NP1 by 2 is the second root in NP. But where is second root from NP1? NP1 there is no second root. Here it's not showing. Perhaps it got missed. Okay, anyway, it's not available. It's none only, no? Here. So NP1 oblique 1 test is none. Actions determine if it finds determiner, current token with its number in determiner and number in registers. This number you store in a register, and then when there is a determiner, that number is stored in let us say one determiner. That in num register. Actually, in num register you store the determiner with its number. Then NP oblique 2 name. NP oblique 2 is here. This is 1. This is 2. 1 is the determiner. 2 is the name. Current token with its number in determiner and number register. Perhaps here this 1 would be stored. DT determiner could be A and the, and this 1. That will be stored. Oh yeah, NP1 has 2 here. Students, NP1, I could not find 2 earlier. Now I could find here. NP1 oblique 1 is this root, this noun. NP1 oblique 2 is this adjective. So it also has 2. when the current token is name along with the number. And then np1 by 1 num and num is equals to null. Then action is taken, else it fails. Num and num is not equal to 5. What does this means? When we are in np1, and we have to go to path number 1, np1 1. When we have to go to path number 1, we have to check that uh, here there could be num. Num means there is, if there is a determiner or not. np1, np2. So num and num star is the register value. Num is the determiner value. If both is 5, means if there is no determiner, then uh, if there is no determiner, uh, this noun is assigned head, uh, assigned a value head, means current token is assigned to head, means that implies that this noun is the head of the sentence. Suppose if it is Alice is uh, cute, then this Alice is the head of the sentence. And then np1 by 2 is for adjective. If there is an adjective, then it is appended. If there is no adjective, also there is no problem. But if there is an adjective, it is appended into this list. If there are more adjectives, if there is one also, it is added to this. If there is second is also added. S naught by 1. What is S naught by 1? This is S naught. This one, S naught. S naught by 1. There is no test. S naught by 1 is the subject. Assign entire structure written from NP network to subject. Here, S naught, when it is taking NP, going to S1. And then whatever is this NP is the subject of the sentence. If I say Alice is cute, Alice is the subject, and Alice is just the name. When Alice is just the name, the second network, noun phrase network, would take root number 2, and make it head of the sentence. Okay. And then S1 by 1 means what? S1 by 1 is this S1. S1, it accepts a noun phrase. Actually, after accepting noun phrase, we have from S1, S0, we reached S1. When we are in S1, it is expected that there is a verb that follows the noun phrase. S1 over 1. So we have to check whether subject is there or not. If subject is there, then if it is not equal to 5, means there is something, then action is taken. 5 means nil, when there is nothing. If there is something, then only action is taken, otherwise action is not taken. If there is a subject and that subject is stored in the register, then what is the action that is to be taken? Main verb is assigned. Why main verb is assigned? It means that the following word is a verb. Then S2 oblique 1. S2 oblique 1 means we have reached S2. First we found noun phrase and then we have found verb. Take an example, Alice runs. Alice runs means Alice is a subject which is parsed under this noun phrase sub network, and verb is runs, which is a main verb which has been found uh, by being in S1. Now we have reached to S2. Runs after run with a with a any object. If we take any object, let us say with a ball. If I say with a ball, then what happens here? Again, another phrase occurs here. With means this preposition. A ball is a noun phrase. Suppose the sentence has only Alice runs. Then from S0 to S1, from S1 to S2, from S2 to S3, it goes by not taking anything, just the jump, just the jump. All right, it just jump without taking anything because there is nothing after verb. And then S0 position is 1, S0 by 1. Which arc it follows? When it is in S0, which arc it follows? When it is in NP, which arc it follows? When it is in NP1, which arc it follows? This is the trace of the parsing sentence. When it is in S0, it follows this S1. When it is NP1, it can go to NP1 by root 1, or it can go to NP2 by root 2. Like that, tracing CNP1 by using root 1, it goes to NP1, or it can go to uh, uh, NP1 using 2. 2 means what? Uh, if you have a determiner and the number of the determiner, okay. The num here is, students, here the num is whether it is singular or plural. Okay. Uh, Head is dogs, the dogs, and the num is plural here, dogs, because it is dogs. And what it is checking here, check singular comma plural, and plural is not equal to 5. Yes, and means plural is there, it is not equal to 5. There is a plural verb. When it is in NP2, NP2 by 1, by using 3, it can return the structure subject, noun phrase, determiner, the head is noun, number is plural. And when it is S1 by 1, it succeeds. The main verb is something, number is plural, main verb is, for which sentences this has been done? Okay, the following registers and notations are used. Num star is the number register, right? Num sub is the subject. Num register uh, in subject. The values of the registers are often used as intersection union of sets. And append adjs means return the list of adjectives. Consider the following sentence. The dogs love John. 1 minute. Okay, the dog love John is the sentence. Dogs is dogs means it is a noun. The root word of dogs is dog, and it's in plural form. It occurs in plural form. Dog is noun, and the root is dog, and the number is singular. Dog means singular. And the is determiner. The root is the only, and the number, it can follow singular or plural. Then love is a verb. The root is love, and the number is plural. If it is loves, it will be singular. John is the name, and the root is John only. This is the lexicon. This is called as lexicon. Why it is called as lexicon? Because it represents the words along with their types, grammatical type, and also their form, whether they are singular or plural. All right. And then implementation of ATN in Prolog. In Prolog language, how to implement? We say start and then colon dash and specify what is the start. And again, one more start is for wrong response or a wrong sentence, and one is for correct sentence. States, what are the states? Because here we use registers, and registers would store the uh, data along with the number. The number here is a singular type or plural type of the word. Final state, when final state we reach, it could be S2 or S3. If there is nothing, S2 could be treated as final state, but it has to jump to S3 to end it. And these are the functions in Prolog. Transition from S0, uh, how you are moving from by accepting AB, how we are moving from S0 to another state. Look at here, set state equal to 1. When it finds properly everything, it set the state to S1. And when it is in S1 and everything is right, it go to S2. Like that, these are transition functions. For every node, there will be a transition function. Okay, that is about augmented transition network. So far, we covered link uh, parser, chart parser, simple transition network, recursive transition network, and augmented transition network. This is another kind of uh, uh, method where statement or sentence could be parsed. This context-free grammar is extending to another type of grammar, which is known as definite clause grammar. And parsing using definite clause grammar is important application of Prolog and logic programming. And it was developed by Perere and Warren in 1980. In this definite clause grammar, the grammar rule in definite clause grammar consists of a left-hand side corresponding to the particular part of ordinary Prolog rules, and right-hand side corresponds to the condition part or body of the Prolog rule. There, like we have rules in context-free grammar. Those rules could be coded in Prolog, and we could write this definite clause grammar with the left and right side of the rule, where left side corresponds to the part of the Prolog rule and right side correspond to the body of the Prolog rule. And these two sides are separated by an arrow symbol. In Prolog, DCG means definite clause grammar rules are transferred automatically into equivalent Prolog rules because they both are closely related. Example is here. This is non-terminal on left hand side of the rule, and here this is sequence of terminal or non-terminal on the right hand side of the rule. S defined as NP, VP. Okay, noun phrase, verb phrase. NP defined as determiner, noun. Here you see rule numbers have been assigned. Noun phrase could be determiner, adjective noun. Noun phrase could be adjective noun without determiner. These are, when we speak, there are various sentences that occur in various forms. Some would have determiners, some would not have determiners, some would have adjectives, some would not have adjective. To model all those, these rules have been defined. Verb phrase, just verb, or verb and noun phrase, and determiners could be and the. This is our context-free grammar. Indefinite clause grammar, DCG rules. In this manner, CFG is defined. How is DCG rules defined? We know that we have left hand side and right hand side, and it is separated by an arrow. A sentence is sentence could have noun phrase, verb phrase. Noun phrase would have determiner, noun. Verb phrase would have this. And then you see this noun, verb, these are extended and written in separate lists. These are separate lists. Example here, consider this example. If the sentence is the girl eats an apple, X is the girl eats an apple, Y is empty list, Z is eats an apple. Separately we have taken the token. Now the sentence is can be represented by the words obtained by subtracting Y from X as follows. X minus Y. X minus Y means this is X minus Y. Y does not have anything. So the noun phrase is uh, same. The girl eats an apple. Whereas X minus Z. What is noun phrase? To get the noun phrase, we have to subtract eats an apple. Why eats an apple? Because eats an apple is beginning with a verb. If a phrase begins with a verb, then it is a verb phrase. If a phrase begins with a preposition, it is a prepositional phrase. If a phrase begins with a noun, it is a noun phrase. Like that, here we know that now boy is a noun, girl is a noun, song is a noun, and eats is a verb, sings is a verb. Because we know that eats is a verb, whenever it encounters eats, it creates a separate list, z. Z equal to eats an apple. So X minus Z will give us noun phrase. The girl. The girl is the noun phrase. And Z minus Y does not have anything. So Z minus Y would give eats an apple, which is a verb phrase. In this manner, we obtain the parsed sentence. Parsed sentence means what? Identifying these phrases and then uh, trying to check whether they are following the format or not. When we were kids, we were taught in school the sentence should follow this format: noun phrase, verb phrase. If a sentence does not follow this format, then the sentence is not right sentence. Same thing we are teaching now to AI system, which is an NLP system that automatically understands the language. All right, students, this is how we obtain noun phrase and verb phrase. And this definite clause grammar rules could be directly mapped to Prolog program. The sentence XY, X is noun phrase, Y is verb phrase, NP is XY determiner noun, verb phrase is verb noun phrase. Like this, directly this could be mapped. There is a For parsing a sentence in Dcg, the normal prolog goal is executed. It's expressed by adding the extra argument by user as follows. Question mark sentence, the girl eats an apple, an empty list that gives us uh, various rules. X1, girl eats an apple. X eats an apple. Y, an apple. Y1, apple. How are you obtaining all this? By using different phrases and then subtracting one from another, we are obtaining different rules. Extra arguments could also be added in this DCG. Sentence 1 of N, uh, noun sentence. NP of N, VP of N. This noun sentence can be, again we have noun noun phrase and verb phrase. In this manner, the definite clause grammars could be extended. And here, this is the proof for the ground rule. The sentence is the girl eats an apple. Sentence is the girl eats an apple. Uh, mm, Here, the girl eats an apple. The girl eat an apple. The girl eat an apple fails. Why it fails? Because it is not matching the number. What is the number? Means whether it is plural or singular. Girl is singular. Because girl is singular, here you have to use eats, not eat. If girl is plural, uh, then you have to use eat. So when you use DCG and try to parse this sentence parsing fails because it is not the right grammar. And the first one passes because it is the right grammar. Here it says the girl eats an apple. Eats is singular, girl is singular, both are matching. All right. Let parse tree. We already discussed how parse tree is created. We begin with a sentence, noun phrase, verb phrase. In noun phrase, what is there? That. And in one verb phrase, what is there? That one. Construction of a parse tree. We construct a parse tree using DCG by you assigning this different values to different phrases. A sentence is having noun phrase, verb phrase. So this is total sentence will have two phrases. And noun phrase representing subject, verb phrase is the action. In noun phrase, we have NP, DN. What is DN? Determiner and noun. In VP, what do we have? Verb phrase, noun phrase. Like this, it is developed, and then DCG rules are formed. In Prolog, if we say P equal to sentence, NP determiner the noun girl, verb phrase in verb eats, noun phrase determiner and noun apple. This is what this is one sentence, and it is satisfying the properties of language, and it is acceptable. And here variable P will have this sentence that has been assigned with the grammar and yeah and the grammatical structures. P equal to sentence. Yeah, a sentence will have a subject. In this way also you can represent. Here, how are you representing the sentence? There is a subject. Subject will have noun phrase, and there is a verb phrase, and uh, apparently there could be an object as well, but this is an optional. So P could be represented in this form. Various ways how you can uh, form English like sentences. All rules you should mention, and these are DCG rules, and these are equivalent prolog rules. Please go through. If you find it any difficulty, if you don't understand, please ask me in tomorrow. Tomorrow we don't have class, no? Uh, eh, Today, Thursday. Okay. You ask me next week. Next week also I will take classes. I will finish this syllabus. Okay, two topics are left over. We'll finish that syllabus, but then um, I want to talk to students. Please stay in the meeting. I'm stopping the recording.